Welcome to Math Vision Tutorial. My name is Moses. Kindly subscribe to my YouTube channel if you are new, and don't forget to click on the notification bell to get notified whenever I drop a new video. In the last class, we talked about electric potential energy. So today we shall be talking about electric potential. Please listen carefully to me so that we can easily get the difference between the electric potential energy and the electric potential. So now, in the last class, we defined the electric potential energy of a charge to be the work that must be done on the charge to bring the charge from infinity to a particular point against an electric field. And the electric potential energy is the potential energy possessed by that charge. That is, the potential energy that the charge has. So now, what about electric potential? Electric potential at a point is simply the work that must be done on one coulomb of charge to bring the one coulomb of charge from infinity to the point against an electric field. Let me come again. Electric potential at a point is simply the work that must be done on one coulomb of charge to bring the one coulomb of charge from infinity to a point against an electric field. So now, comparing these two definitions, we can see that the two definitions are quite similar, but here is the difference. For electric potential energy, it is the energy that is possessed by the charge, that is the energy of a charge. But when we talk of electric potential, we calculate electric potential at different points in space. We calculate electric potential at points in space, while we calculate electric potential energy of a charge. So now, at different points in space, we have different electric potential. Like we define electric potential, we said it is the work that must be done on one coulomb of charge to bring the one coulomb of charge from infinity to a point or to the point against an electric field. So now, at different points in space, we have different electric potential. And from the definition, it can be easily seen that when you are asked to calculate the potential at a point, the potential at a point simply means that what is the potential energy that one coulomb of charge must have at that point. That is the meaning. Electric potential at a point, it simply means that what potential energy must one coulomb of charge have at that point. Let's go into the definition on the board. We have that the electric potential, denoted as V, is simply the work that must be done on a unit charge. Unit charge means one coulomb of charge, a charge that has the magnitude of one coulomb. The work that must be done on a unit charge to bring the charge from infinity to a point RA against an electric field. Now we said, in other words, from this definition, we cannot see that we say it is the electric potential energy, yes, that one coulomb of charge must have at a particular point. The electric potential V at a point is also seen as the potential energy, as the electric potential energy that one coulomb of charge must have at a particular point. And we can also see that it means potential energy per charge. So now we can see that the electric potential is related to electric potential energy. So electric potential is simply the electric potential energy per charge, and that is why the unit of electric potential is joules per coulomb. So now let's see some illustration. Notice that charges create electric potential. Remember that charges create electric field. So also do charges create electric potential. Consider this positive charge. At every point in space around this charge, we have different electric potential due to this charge. Due to the presence of this charge, we have electric potential at every point in space, and the closer the point to the charge, the stronger the electric potential, or the higher in magnitude of the electric potential. Points that are very far away from the charge, we have low electric potential, but points closer to the charge, we have strong electric potential. Charges create electric potential at every point around itself. So now, at this point, we may say that there is a magnitude of an electric potential has a magnitude of 10 joule per coulomb at this point. This means that at this point, 1 coulomb of charge possesses a potential energy of 10 joules. That is, at this point, 1 coulomb of charge possesses 10 joules of energy. So at this point, we may have that electric potential at this point is 30 joules per coulomb. It means that 1 coulomb of charge has a potential energy of 30 joules at this point. So that is how to view electric potential. Electric potential at a point is the amount of electric potential energy that 1 coulomb of charge must have at that point, and that is why we have the unit to be joules per coulomb. So now, how do we derive the magnitude of electric potential? We derived the magnitude of electric potential energy in the last video. So how do we go about the magnitude of electric potential as well? So now, remember that electric potential is potential energy per charge. So we have that electric potential, which is denoted as V, is the potential energy U per charge. But we know that the magnitude of the electric potential energy as derived in the last video is simply K multiplied by Q1 Q2 over R. So now we can replace the value for U in equation 1. Let's call this equation 1. So now we now have that the electric potential V is K Q1 Q2 over R, which is this, divided by this Q now, divided by Q, and this is simply times 1 over Q. So now, this Q, we cancel one of the Q in the numerator. So we finally have that the magnitude of electric potential now is KQ over R. And this is denoted as the magnitude of electric potential at a point due to the charge Q at a distance to the charge. So this is the magnitude of electric potential at a point, yes, at a point due to the charge Q. So now we shall look into the relationship between electric potential V and electric field. There's a relationship between electric potential V and the electric field E. Now, we want to show the relationship between the electric field vector and the electric potential. Remember that the electric field is a vector quantity, while the electric potential is a scalar quantity. So now, we shall begin with the work that must be done to move a charge between 2 points against an electric field. That is the work done to move a charge between 2 points R1 and R2 against an electric field. And we know how to do that. We know that we have to take the tiny work done along the path from R1 to R2 and sum the tiny work done to get the total work done on the charge from R1 to R2. And the process of summing up the tiny work done led us to the integral of f dr. Yes, the process led us to integrating f dr from R1 to R2. So now, we have that the work done is the integral of F dr from R1 to R2. And what is the force in an electric field? The force on the charge in an electric field. Remember that an electric field E is simply F, the force, per charge. So cross multiplying, we have that the force is electric field multiplied by Q. So we are going to replace EQ for the force in the above equation. So now we have that the work done now is the integral of EQ dr from R1 to R2. So the Q is a constant, so we can take out the Q from the integral, and we have that the work done now is Q integral of E dr from R1 to R2, and this is the work done to move the charge from R1 to R2. So now, from the principle of work energy theory, we have that the change in potential energy is equal to the negative work done. Yes, the change in potential energy is equal to the negative work done according to the principle of work energy theory. So now we have that the change in U, which is the potential energy, is negative work, and the work is simply Q multiplied by the integral of E dr from R1 to R2, and this is negative Q integral of E dr from R1 to R2. This is a vector. So now we have that the change in potential energy is negative Q integral of E dr from R1 to R2. And we know that electric potential is electric potential energy per charge. So change in electric potential also will be change in electric potential energy per charge. That is, change in electric potential will be change in electric potential energy per charge. So our change in potential now will be change in electric potential energy. Our change in electric potential energy is negative Q integral of the electric field vector dr from R1 to R2, which is negative Q integral of electric field vector dr from R1 to R2 over Q. So now this Q can easily cancel this Q, and we have that our change in electric potential, which is change in V, is negative integral of the electric field vector dr from R1 to R2. So the change in electric potential is this, but we want to find the electric potential at a point and not the change. How do we find the electric potential at a point? So now, if we consider point that is infinitely far from the charge that is creating the electric potential, we will see that the point that is infinitely far to the charge that is creating the electric potential, we have its electric potential to be 0. Remember that points that are closer to the charge that is creating the electric potential, the point we have strong electric potential. But points that are very far away from the charge that is creating the electric potential, we have weak or low electric potential. Points that are far from the charge that is creating the electric potential, we have weak or low electric potential. But points that are very, very far, that are infinitely far from the charge that is creating the electric potential, we have their electric potential to be practically 0 because they are very far. So at points that are very far, we are going to have electric potential to be practically 0 at points infinitely far to the charge that is creating the electric potential. So now we know that the change in V simply means V from the potential at point R2 minus the potential at point R1, that is the final potential minus the initial potential. So let's assume that we start the initial potential from a point that is infinitely far from the charge that is creating the electric potential. When we start from a point that is infinitely far, we will see that the potential at that point that is infinitely infinitely far to the charge that's creating the electric potential, we see that the potential will be zero. Yes, the potential at the point that is infinitely far to the charge will be zero. So now, since the point, okay, here we have a final potential minus initial potential will be negative integral of the electric field vector dr from R1 to R2. So now, when we start to move the charge from a point that is very far, then we know that the potential at that point will be zero. So now we now have that the final potential is R2 minus 0, which is equal to negative integral of E dr, starting from point very far. We don't know the point can be any point. So we say it is infinitely far, the point that is infinitely far from infinity to R2. So now finally we have that the potential at R2 now, at point R2 is negative integral of E dr from infinity to R2. Or let me put it up so that we can see it clearly. So we have that the potential at R2 now is negative integral of the electric field vector dr from infinity to R2. So now this is the potential at R2. This is the potential at point R2. So we cannot generalize this as the potential at any point is simply the negative integral of E dr from infinity to a point R. Yes, to a point R in the electric field. So this is the relationship between the V and the electric field vector. So now this is also the magnitude. Remember that in the last section we derived the magnitude of electric potential, but the magnitude of the electric potential in the last section does not have any relationship with electric field. We only derived that to be V equals to KQ over R. That is the magnitude, and this is also another magnitude, but this magnitude is having relationship with the electric field. And we have that the magnitude of electric potential is simply the negative integral of the electric field vector dr from infinity to the point of consideration. So now, how do we find the electric field from the electric potential? How do we make electric field the subject of formula? How do we find the electric field vector from this? The way we can find the electric field vector is to differentiate both sides. We have to differentiate both sides. Remember that in mathematics, when we have f of x to be equal to cos x, if I integrate f of x, then I'm going to have sine x. So now, when I differentiate, so differentiating this, that is, when I differentiate with respect to x, I differentiate this, I'm going to have cos x, and cos x is f of x. So this means that when I differentiate this, I'm going to have f of x. This simply means that d dx is the inverse of this integral. That means taking the differentiation of this integral, this we cancel this, and we are going to be left with f of x. So applying this technique to this now. So by the time we differentiate both sides with respect to her, that is d dr of v, we are going to have this to be d dr of the negative integral of e dr from infinity to r. So now this means that this d dr we cancel this dr, we cancel this dr, and this d we cancel this integral sign. So now we are going to be left with d dr of v, which is equal to the negative electric field vector. Transferring this negative sign to the other side, we are going to have an electric field vector is equal to the negative differentiation of d dr of v. So now, this is not all. Don't forget that the curve we are considering now is along is having three coordinates. It's having the x, y, and z coordinates. So we have to differentiate this scalar field along the three coordinates. So now we differentiate. So that means we are going to have the components of the electric field in three places. So we are going to have the electric field along x to be negative d dx of v, the electric field along y to be negative d dy of v, and the electric field along z to be negative d dz of v. So now the electric field vector now is the electric field along x plus the electric field along y plus the electric field along z. So now it's a vector quantity. So writing the electric field vector now, we are going to have the E of x. Now the Ex now is negative d dx of v now plus negative d dy of v plus negative d dx, dz of v. Okay, we have our I and j, we have our y, j, and k. So now from this, by the time we take out negative v from this equation, taking out negative v, we are going to have, taking out negative v, we are going to have that the electric field vector now is d dxi plus d dyj plus d dzk negative v. So we are going to have negative v outside. So this expression in the bracket is called the grad, yes, and it is denoted with the symbol called nabla. The symbol called nabla. So now we now have that the electric field vector now is nabla multiplied by negative v, and now our electric field vector is negative nabla v. Yeah, where this nabla is called the grad, and nabla is simply this expression over here. So now this is the relationship between the electric field vector and the electric potential. So now we are going to stop the class at this point. So in the next video, we shall be looking at the examples. We shall be looking at some examples under the electric potential, the electric field, and the electric potential energy. If you find this video helpful, kindly share the video across to your loved ones, and don't forget to subscribe to my YouTube channel, and also click on the notification bell to get notified whenever I drop a new video. Please watch over and over again, and I'm going to see you in my next video.